Talking about something called a mole ratio. Okay, a mole ratio. Mole ratio is a conversion factor that helps us relate amounts of moles of any two substances in a reaction. So it allows us to compare, if I put in 2 moles of this, how many moles of my product can I get out? Okay, it allows us to look at how our reaction has to fit together to be balanced. Okay, so here's an example of a chemical reaction. We're going to start looking at the mole ratios here, but before we even answer that question, before we even talk about mole ratios, tell me, what type of reaction is it? Don't shout it out just yet. Think about what type of reaction it could be. Combustion, synthesis, decomposition, single displacement, or double displacement. Okay, what type of reaction could that be? Don't shout it out yet. Raise your hand if you think you know. Raise your hand confidently if you think you know. I only see about 4 hands raised. Okay? All right, Benedict, tell me what it is. Decomposition. I would agree. Why is it decomposition? It's breaking down, right? We have one big thing that breaks apart into 2 smaller parts. What's the opposite of a decomposition reaction? Synthesis reaction. Synthesis reaction builds it up. Decomposition breaks it down. Okay, very good. It is a decomposition reaction, okay? I want to start looking at mole ratios here, and I want to talk about what these coefficients in front of the problem mean, okay? These coefficients in front of the problem not only tell me information about what happens at the molecular level, so I put 2 molecules of KClO3, and I can break it down to form 2 molecules of KCl and 3 molecules of O2. But those coefficients also tell me what happens at the molar level, so at a bigger quantity of that. This tells me if I put in 2 moles of KClO3 and I break it down, I would form 2 moles of potassium chloride and 3 moles of water. Okay, so all of that information works at both the molecular level, the smallest little individual molecule level, but it also works at the molar level, which is really where we will work. Okay. All right, let's balance the equation first, and then we're going to answer some questions about mole ratios. What is the ratio between these 2 atoms? Okay, so let's try to balance it first. I'm going to give you just a minute or so to balance it, and then we'll check. Okay, so try to balance that equation first. If you can do it without the list, that's going to save you a little bit of time, but do whatever you need. That's how I ended up balancing it. 1, 2, 1, 2. I don't know. Tell me if you think that's right or wrong. Good? Okay. The first place I started with was nitrate. Right? NO3. There's 2 of them here. So it had to start me with a 2. That makes it 2 silvers. So I come over here and say that's 2 silvers. And then I just check my last one, which was copper. Can anyone figure out what type of reaction that is? So I heard someone whisper it. Single displacement. I would agree. Single displacement, right? One object is getting switched, right? Copper and silver, so switch places there. So single displacement. Okay, now it's asking us, what is the mole ratio between copper and silver? All we're going to do here is look at the coefficients. Okay, what is the mole ratio? So the mole ratio of copper, what's our coefficient that's going to go right there? If there's nothing there, we assume it's a 1. So the ratio is 1 to 2, right? Because I have 2 moles of silver. The ratio is very simple. We're just looking at the relationship between one and another. So this says, in order for the reaction to take place, I need 1 mole of copper plus 2 moles of silver nitrate to yield 1 mole of copper nitrate and 2 moles of silver. So we can write the ratio a lot of different ways, just as a ratio like that, like you do in math. Does that look familiar, writing a ratio that way? Okay, you can write it like that, but the way we're really going to use it is in a T-chart. Okay, so I'll walk you through what that will actually look like. Okay. So let's start with our most simple stoichiometry calculations. This is converting moles of our substance to moles of a different substance. Okay, mole to mole. This is when we take the amount of our substance in moles and we convert it to moles of a different substance. These are our easiest type of conversions, okay? So let's go ahead and balance this first, and then we're going to answer this question below. Okay? This is a little tougher balancing because it doesn't have all of our polyatomic ions that stay together on both sides. Okay, so we're going to have to be a little bit more careful with how we balance this. I don't know. Maybe that's all it takes. Is that what you guys have? Okay, so this 3 only applies to the oxygen, right? That's okay. I think this might be balanced. 2 lithiums, 2 lithiums. How many oxygens? 1, 2 plus 2 more is 4. So 3 plus 1 is 4. 2 hydrogens, 1 carbon, 1 carbon. So I think that's actually balanced just with that 2. Okay? It asks us for what type of reaction it is. Do we have any idea? I'd probably call it a double displacement. It's a little bit unclear because our polyatomic ions don't stay exactly together, but we do see a switch there. Okay? But let's go ahead and answer our stoichiometry question. How many moles of lithium hydroxide are required to react with 20 moles of carbon dioxide? Okay, so with any T-chart, we always start with what? What we know, okay? And what we know in this problem is that we have 20 moles of CO2. 20 moles of CO2. And our goal is to find out how many moles of lithium hydroxide we have. So I'm even going to come up to my problem here, okay? And I'm going to write just some help for me, right? I'm starting with 20 moles of this CO2, and my goal is to find out how many moles of lithium hydroxide I have, right? Writing it above the problem gives me kind of an area to kind of zone in on, right? It allows me to focus in on what mole ratios I'm looking at, okay? So we're going to start our T-chart with what we know, and we draw the T, okay? If moles of CO2 is here, in order to cancel it, it has to go here. Right? That's how it always works in our T-chart. What we want to cancel has to go diagonally. Would we agree with that? Okay, but what am I trying to get to? Moles of lithium hydroxide. Now, this is the only step in which we can do this. We can go moles of lithium hydroxide. This step right here is called the mole ratio step. And it's the only place in our T-chart that we can have 2 different compounds in the same column. The only place that we can change over from one compound to the next is mole to mole. Okay, that's the only place we can do that. We cannot compare grams of one to moles of another. We just can't do it. 1 gram of hydrogen would be a whole mole of hydrogen, right? But 1 gram of water would only be like 1/16 of a mole. So we can't compare grams of one to grams of another, or grams of one to moles of another. The only place that we can switch is if they are mole to mole. So this is called the mole ratio step. Where these numbers come from now, that go right here, this is the only place in our T-chart where moles won't get the 1. These numbers come directly from our balanced formula, our balanced equation. So I'm going to come up and look at what is the coefficient that goes with CO2, and that's going to go right there. So what coefficient does go with CO2 in our problem? 1. So moles of CO2 is 1. How many moles of lithium hydroxide? 2, right? That number comes directly from our balanced chemical reaction. And so there I'm going to check my work, right? I've canceled moles of CO2. I'm left with moles of lithium hydroxide, which means I would need 40 moles of lithium hydroxide. Now I want you to look back at the original problem. Does that seem to make sense? Does that ratio match? Don't I have twice as much lithium hydroxide as I do carbon dioxide? Right? So our ratio is very simple. But when our problems become more complex, then it's not going to be as easy to just like see it and say it, right? We have to build out this process of our conversion. Okay, so that's this step right here, where we convert moles of one to moles of the other, is called the mole ratio step. And we might start our problems later with grams or end them in grams, and so we'll build that out. But the mole ratio step's the only place that you can change from one compound to another. Okay, moles. All right, any questions with that so far? Okay. Okay, let's look at our next mole to mole conversion. Okay, let's balance this one real quick. And we'll find out how many moles of O2 can we form from decomposition of 5 moles of hydrogen peroxide. Okay, so let's balance first. Okay, everyone most people are looking up, so that means we're good with balancing, right? I knew this oxygen had to become an even because over here I'm never going to have an odd number of oxygens, right? So I started there. That gives me 4 hydrogens. So I need 4 hydrogens over here, which is good. And that means I have 4 oxygens and 4 oxygens. So all good. All right, this asks me how many moles of O2. So I'm looking for moles of oxygen gas will result from the decomposition of 5 moles of hydrogen peroxide. So which one of those is hydrogen peroxide? It has to be H2O2, right? It has to be this one because I already know that this is water. I know that's oxygen gas. I'm not sure what the name of that one is, but I can use context clues to figure out which one it is. Does that make sense? Right? Process of elimination tells me the hydrogen peroxide has to be H2O2. So I'm starting with 5 moles of that. All right, I'd start my T-chart with what I know. 5 moles of H2O2. And I make my T-chart. Right? Moles of H2O2 has to go here on the bottom. And I'm going to moles of oxygen gas. Right? And what's this step called? Mole ratio step, right? It's the only place that I can have 2 different compounds in there, right? I know when we first did conversions, you guys left off like the name of the compound, but it's going to be really important that we carry that all the way through our process, because if we don't, we're going to start getting confused about that's moles of what, or that's grams of what, right? We have to carry the name or the formula for our compound all the way through that chart, okay? Then where do these numbers come from here? They come from the chemical equation. So H2O2 is going to get what? A 2, and oxygen gas is going to get a 1. Okay, so to solve this, I multiply across the whole top, divide by the whole bottom, and I get 2.5 moles of O2. Does that seem like it fits the ratio that we laid out? Okay, that's why we said these mole-to-mole conversions are the simplest, because we can see usually a really clear picture of what our expected answer is supposed to be. All right, but now we're going to add in the gram component of it. Now we're going to ask ourselves to go all the way to mass, right, and use that molar mass for our compounds and take it a step further. Are there any questions on the mole-to-mole conversions, or do we feel pretty good about that? Okay. Now we're going to look at gram to mole conversions, okay, or mole to gram conversions. So let's start with balancing, and then we'll get to work on the actual stoichiometry part of it, okay? So let's go ahead and balance it. Well, we don't have any numbers information. It's just saying it's reacting with carbon dioxide. So there's nothing that we have to put in differently in our T-chart about that. Okay, this step right here is called the mole ratio. And so those numbers come directly from our chemical reaction. So water is going to get a 6. And what's glucose going to get? A 1, right? Because there's no coefficient listed there, so we assume it's a 1. Now we come over to this part, which is just converting moles to grams, which this is what we've always known how to do. So this is the step where we go back to moles always getting the 1. Okay? Moles and grams, we go back to moles always gets the 1. Because this molar mass does not tell us how many grams is in 4 moles of it or 6 moles of it. It tells us how many grams is in 1 mole of it. Okay, so let's find the molar mass of glucose and plug it in there. So let's go ahead and get your calculators out. I want to see everybody trying to solve molar mass for glucose there. So 180 grams per mole. Before I do the final math, I'm going to check my units one more time. Did I cancel moles of H2O? Yes. Did I cancel moles of glucose? Yes. I'm left with grams of glucose, which is what I wanted. So now I just do the math. Multiply across the whole top, divide by the whole bottom. And so that gives me a value of 90 grams C6H12O6. Right? We want our final answer to have both the number and the unit and the formula. Right? We have to tell, what does this number mean? Right? It's 90 grams of that product. That seem simple enough? That T-chart is going to work in any direction with any combination of things. The mole ratio step is the only new step for us, and that's where we switch over from one compound to another. Okay? I want you to try the next one here on your own. I've already got it balanced for you. I just want you to try the stoichiometry on your own. How many grams of water are produced if 2.2 moles of NH3 are combined with excess oxygen? What's the word excess mean? Extra or leftover, which means we're not concerned with oxygen, right? We're just talking about what we do know. Okay, so I'm going to give you a few minutes and then I'll get it started up here on the board as well. How many grams of nitrogen, NO, nitrogen monoxide, is produced if 12 grams of O2 is combined with excess ammonia? Okay, so we've got to identify which compounds we're really focusing on, right? How many grams of NO, so that's going to be my question mark, okay? How many grams are produced if 12 grams of O2? Okay, excess ammonia, that doesn't mean anything. Ammonia is this guy right here. It just means we have extra of that, so it's not affecting our reaction, right? That's all that really means. So this is a gram to gram conversion. So that means we're going to start in grams of O2, and we want to end up with grams of NO. Okay, sorry, I couldn't remember which one it was. We want to end up in grams. So we've got to stretch our T-chart one more section. Okay, we're going to start with what we know. 12 grams of O2. We want to get rid of grams of O2, but what do we need to go to? What's our middleman between these two things? Moles, right? I have to get to moles. So I'm going to go moles of O2. Now, do you guys prefer to fill in the numbers as you go, or do you rather fill in the numbers at the end?
I have to do it as I go.
As you go. Okay, so let's just go through that process too, okay? If I'm going to fill in the numbers as I go, I know the molar mass of oxygen gas has to go there. The molar mass of O2, which would be 32, right? O2 is 16, and we have to make sure we account for 2 of them. But in this step, what does moles get? Does it get a 5?
Yeah.
No, in this step, moles gets the 1, right? Because we're still saying that 32 grams is equal to 1 mole of O2. Okay? Mole ratio step is the only place you put in those coefficients. So now I'm going to keep working, and I'm going to get rid of moles of O2 and go to what? Moles of NO. So here is our mole ratio step right here. Okay, this is the place where we can make the change from one compound to another. And so these numbers come directly from the reaction. So 5 for O2 and then 4 for NO. Okay, are we clear with where those numbers are coming from? We're leading with our units to figure out how our T-chart has to go, right? I want to get rid of grams and go to moles of O2. I want to get rid of moles of O2 and go to moles of NO. I want to get rid of moles of NO and go to what? Grams of NO. Okay, so we're going to always make sure that we lead with our units. Moles of NO to grams of NO. And here we're back to moles getting the 1. And that molar mass is somewhere around 30, I think. 14 plus 16 should be 30. So now, again, I'm going to check my units one final time. Grams of NO cancel. I'm sorry, grams of O2 cancel. Moles of O2 cancel. Moles of NO cancel. Grams of NO, which was what I was trying to go to. Right? That should always be on my top right. So now I'm going to multiply across the whole top, divide by the whole bottom. And I get a value of 9 grams of NO. Okay.